All right, two things I want to mention right off the bat as we get started. So the first one is I'm going to go pretty quick through the math on this, and that's because the focus for this is how do you set up these problems, not how do you solve the algebra. We've been solving the algebra for a while. So if you're having trouble with that part of things, please let me know because I do want to help with that. But I also want to make sure to focus on what we need to go over here, which is how do we start solving these 2D problems. The second thing is if there's something that you're having trouble with or that I seem to gloss over, because I'm going to be going over a lot here, make sure to send me a message, let me know, so I can help you out with that. So number one, describe the horizontal and vertical motion of an object that is fired off a cliff parallel to the ground. So this is actually similar to the lab we did. So here's my object. Okay, it's fired horizontally, and it's going to make some kind of curved projectile path, something like that. Okay, and describing the horizontal motion, so if you think about the lab we did on the computer, the projectile motion lab, you'll remember that the X arrow stayed the same the whole time. No matter what we did, the X arrow was the same, and that's because the X direction is a constant velocity. And the Y direction increased over time. So it started off fairly slow, and then, well, 0 to begin with. And then, sorry, there we go. And then over time, it builds. And so that is free fall from what we talked about last chapter. All right, describe the effect or lack thereof x velocity has on the y velocity. So we are on the y motion. So we did this when we talked about the bullet drop versus bullet fired example. So the bullet dropped would hit the ground at the same time as the bullet fired because both of them are acted only on by gravity. And since gravity is the only thing acting on them, they'll fall at the same rate. So x has no effect on y. Maybe more specifically, the x velocity has no impact on the y motion. But the x and the y you kind of have to treat separately as each other. They're not going to be able to mix with one another. Okay, so let's go ahead and start on the example problem. We'll come back to number 3, and we'll kind of do 3 as we go through the problem. But let's go ahead and get started on the first part of the problem. So, standing at the top of a 6-meter diving platform, Jalen runs straight off the edge with a velocity of 3.5 meters per second. Draw a diagram of the situation. How long did it take to reach the pool? How far out did Jalen land, assuming the edge of the platform is even with the edge of the pool? And D, what's Jalen's velocity right before splashing into the water? So, the first thing we need to do is figure out what do the diagrams need to look like. So this is the first bit for number 3, which is how do we draw the diagrams? So when you're drawing the diagrams, you need 3 things. So first of all, you need to draw the motion that the object's going to have. The second thing you need to do is you need to label the knowns and unknowns. Specifically, though, the givens in the problem, you need the numbers that are given in the problem you need to write down. And lastly, you need to label and identify the positive and negative direction. All right. So now that we're ready to do the diagram, let's go ahead and do the diagram. So I'm going to start off by drawing my diving platform. And let's give us some more room. Drawing my diving platform. Here's the water. Here is Jalen. And I want to label the numbers that are given in the problem. And there's 2. Standing on top of a 6-meter platform and running off with a velocity of 3.5. So if I'm running off with a velocity of 3.5, that's going to be forward. I have a 6-meter platform, so that's how far I'm going to go down. And then I need to draw the motion, so it's going to be a curved path, because that's what all projectiles do. They all travel curved paths. Last thing we need to do is identify what direction is up and what direction is down. So positives and negatives. I like to call the direction of motion positive, so since the motion is down and forward, we'll call down positive. You don't need to call forward positive also, because we're always going to be going forward. So you never need to identify forward or backwards for the x direction, because forward will always be to the right. Backwards, the negative will always be to the left. But you will need to do that for the y direction. And I'm going to go ahead and call down positive, just because I like to call the direction of my motion positive. All right, so now we're done with the diagram. Now we're ready to solve for how long it took to get to the surface of the pool. So I'm looking at the things here, and I'm saying, okay, how long did it take? That's time. The problem gave me a velocity and a displacement as well. Notice that my displacement is positive because it's falling 6 meters, and I called down positive, so make sure you're careful there. So I'm looking at this and I'm saying, all right, so I got my equation list that we came up with, and I'm looking at these equations and I'm saying to myself, oh, V equals d over t. So 3.5 equals 6 over t. If you solve that, you're going to get an answer for t to be some value that I wrote down and cannot find. You're going to get 1.7 for t. However, this is wrong. And I did it wrong on purpose, because I want you to see what will not work. So what won't work is combining our x and our y things. See, this is an x velocity, but this is a y displacement. I can't do x and y things together, okay? They're like different groups of friends. They don't mix, okay? Just some people don't mix. X and y don't mix. So you can't combine them together. So we need a different way to do this, because this is not going to work. And again, x and y don't mix. So what we're going to do is make an x chart and a y chart to try to separate these things. So the second thing we need to do after the diagrams is we need to figure out how to do the knowns and unknowns. And the first thing we need to do with knowns and unknowns is remember to make an x and y t chart. Okay. Once we made the x and the y chart, now we're going to start plugging in the knowns and unknowns. So I'm going to make an x section and a y section. So I'm looking at this 3.5, and I'm saying that 3.5 is in the x direction. So I'm going to write v equals 3.5 in the x column. Okay, 6 is a downward displacement, so that's in the y column. So I'm going to write d equals 6 meters in the y column. And notice that the reason it's a positive 6 and not a negative 6 is because I called down positive. So make sure you're being careful on that when you're doing that. So let's go ahead and add that to our important concepts, important ideas. So be careful with signs. So we've got those things, and now we're ready for our first unknown value, which is time. But I'm not really sure where to put time, because Is time an X thing? Is it a Y thing? Is it up and down? I don't really know what time is. Well, the reason I don't know what time is because time doesn't have a direction. Time is just a number. It's a scalar. So because it's just a number and it doesn't have a direction, we're just going to write t in each column. In other words, it doesn't matter what I use to solve, whether it's x or y. T is the same. And that kind of makes sense, right? It should take the same amount to go forward from start to finish, and it should take the same time to fall from start to finish, because the forward motion and the horizontal motion, or sorry, the forward motion and the vertical motion, while they're independent of one another, they occur at the same time. So they must have the same time. Okay, so we got that figured out, but now we're back into trouble again of not really being sure what else to do here. So while I think about that, let's add one more thing. So we talked about time. So t goes in both columns. So the thing I decided upon is I decided that let's write down all the things that I could have. So x direction is constant. So the things I could have are v, d, and t. So I don't have d. I'm going to add that to the list. And if you're wondering what that d is the how far forward I would go. Okay? That's the only other thing in the x direction. In the y direction, we can have d, we can have t, we can have a, we can have vi, we can have vf. So there's not really anything else I can do in the x direction. I'm pretty much stuck there without knowing that d, and there's no way to figure it out easily. So I need to start thinking about the y direction. If I knew two of these three things, I could start solving. So one of them popped in my head here, and that is, oh, I said on the front page that the y is free fall. And if it's free fall, that means A is 9.8. Not negative, because I called down positive. If you called down negative, then yes, it would be negative. But I called down positive, so that's why I'm using positive 9.8. So that is another thing to add here about knowns and unknowns. A equals 9.8 in y direction. Y direction, not y direction E. And that is always all right. So all I need now is to identify either the initial or the final velocity. And I'm tempted to say the final velocity is 0 because he lands in the water. But remember, it's always right before it hits. So v final is not 0. So I'm looking at this drawing again, and I'm saying, well, the 3.5 is forward. So if the 3.5 is forward, how fast is he going up and down? Well, he's not. There is no up and down motion. So if there's no up and down motion, the initial velocity would be 0. And that's the last thing to add here to our knowns and unknowns section is vi equals 0 in the y direction if the motion starts horizontal. All right. So now we're going to move on and we're going to solve the parts now in part 2. So I'm going to pause here. I'm going to pick right back up part 2 on how to solve horizontal 2D motion problems.